Welcome back to ECE 442-542. Today's segment I'm entitling Competing Performance Specifications, and by that I'm meaning what do we do if we have several performance specifications for our discrete time system that maybe on first calculation don't give us exactly a simultaneous solution that satisfies all three performance specifications. What do we do? Well, the answer is to modify one or more of those specifications. Hopefully we can modify it in the direction that still satisfies each of the individual performance specifications. And it's probably easiest to think about that or to understand this concept by looking at an example where this example will now exercise or impose all three design specifications to try to find complex pole pairs that satisfy the three specs. And just to give us something to think about, let's go ahead and assume that we have a sampling period or a sample period of 0.01 seconds or 10 milliseconds. Suppose we're given the following three performance specs. We have a settling time of 500 milliseconds or less. Suppose we have a percent overshoot of 20% or less, and we have a peak time of 100 milliseconds or less. And again, what I'm hoping that you start to do when you see these performance specifications in front of you, maybe you will start to say or see these geometric figures associated with the different settling performance specifications. For example, on the settling time, you should be thinking or seeing concentric circles, and the smaller the circle, the faster the settling time. 4% overshoot, again, these are in the Z-plane. For a percent overshoot specification, now we are looking at hearts or logarithmic spirals, and as you want a smaller percent overshoot, now you are requesting or wanting that logarithmic spiral or heart shape to be shrinking or collapsing down to where it gets closer and closer to the real axis. So that's the percent overshoot spec. And the peak time spec, the shape that you want to be seeing there would be angles. So that now, if you had these two different angles, this larger angle would correspond to a peak time that was less than the peak time associated with the smaller angle. And in this case, the shape that I'm expecting you to think about is either this angle or wedge type shape for a peak time specification. Now, with these three, what we would ideally like to have happen is that all three are simultaneously satisfied when we find a settling time of 500 milliseconds, a percent overshoot of 20%, and a peak time of 100 milliseconds. But you can anticipate, because this is our example to illustrate competing performance specifications, that that may not be true. But let's now walk through that process and see what we might do in order to make these three geometric shapes coincide, or at least give us a collection of shapes that will satisfy all three performance specifications simultaneously. In this case, with performance specification number one, we have a sampling period of 0.01 seconds, and we're given a settling time in an absolute amount of half of a second. We can then solve that for the sampling period. N sub s is now the ratio of the settling time in absolute terms, half a second, divided by 0.01 or 1 over 100, or we're now taking half of 100 to give us the number of sample periods. This is now 50 sample periods we want at the maximum to satisfy our settling time specification. And we know for a 1% settling time that we need to hit that radius or raise that radius to the n sub s power, and that will then collapse us down to 1% of where we started. Or r raised to the n sub s is now 0.01 or 10 to the minus 2. We're given n sub s, the right-hand side is on us, 0.01 or 10 to the minus 2. We can now solve that for r sub s by looking at taking the log base 10 of both sides of that equation and the log base 10 of the right-hand side. Logarithms are just exponents, and since we're writing it 0.01 is 10 to the minus 2 is on the right-hand side, and the property of powers and logarithms allows us to pull that exponent out in front of a log, so that we now have n sub s log base 10 of r. We have dividing both sides by n sub s, log base 10 of r is equal to minus 2 over n sub s. We can raise both sides, or have both sides raised, or use both sides, or take the anti-log, maybe I'll just say that, of both sides. We now have r is equal to 10 raised to the right-hand side, which is minus 2 over n sub s. 10 raised to the minus 2 over 50 now gives us, or produces, a radius of 0.912. And that's now consistent with a settling time. If we have a settling time, we have to have a stable system, so an r value less than 1 has to be what's happening. Our percent overshoot specification now, we said we wanted a 20% overshoot at the most, and we now use this formula for zeta. You could also look this up on a curve that connects the percent overshoot relative to the zeta value. But here, 20 divided by 100, or the argument of these natural logs, is now 0.2. We square that, divide by pi squared plus the natural log of 0.02 squared, take the square root, and we end up then with a zeta value of 0.456. With a zeta value of 0.456, then we could, in fact, find this intersection of this logarithm of 0.456, this logarithmic spiral curve of 0.456 with this radial distance away from the origin of 0.912, and find that intersecting point to give us our complex pole location. But we would have to interpolate between a zeta value of 0.4 and a zeta value of 0.5, and that might get a little funny. You could have MATLAB generate such a logarithmic spiral and find where that logarithmic spiral intersects with a radius of 0.912, and you would be done. But it's cleaner, maybe algebraically or analytically, to use that zeta value and that r value to compute an angle that's consistent with r of 0.912 and a zeta value of 0.456. And to do that, we can just rederive that rather quickly. We have S in the parameterized form for a complex pole pair is minus zeta omega sub n. Omega sub n is the natural frequency. That's the distance away from the origin. Zeta is our damping ratio, and omega sub d is the imaginary component of S, where omega sub d, the damped frequency, is now this omega sub n times the square root of 1 minus zeta squared. We map that into the z-plane. We have z is equal to e to the st. We multiply that exponent by t, and we can now separate that exponent into two pieces, again using these exponential these properties of exponents. We now have e to the minus zeta omega sub nt as this radius r, and we have our angle theta sub d, e to the j theta sub d, where theta sub d is omega sub d t, where omega sub d is really just this scaled natural frequency, omega sub n square root of 1 minus zeta squared. Now Now, what we don't know in this right-hand side, we know R from performance specification number 1. We know zeta. We don't know omega sub n and t. But we can find those by now using what we already know with R. We know R and we know zeta, so we can now solve for omega sub nt. Capital T, we actually know that was given. What we don't know is the natural frequency. But if we know R is e to the minus zeta omega sub nt, we can then solve for this product, omega sub nt, where we do or don't need to know capital T. So taking the natural log of both sides, we end up with natural log of R is equal to minus zeta omega sub nt. We divide both sides by minus zeta, and we end up now with an expression for omega sub nt, which we will now be able to use in our angle theta sub d formula, since we know zeta, and now we have an expression for omega sub nt in terms of R and zeta. We now have the angle theta sub d. And once we have R and theta sub d, then we are good to go in terms of finding that point or points for these two complex pole pairs. They are at R at an angle of plus and minus theta sub d. The real part being R cosine of theta sub d, the imaginary part being R sine of theta sub d, where theta sub d now is omega sub n or omega sub dt. Maybe I should have said that here. This is now omega sub dt, where omega sub d is, in fact, omega sub n times t square root of 1 minus zeta squared. We replace the factors that we know numerically, capital R and zeta, and we can compute then theta sub d to be, and so now I see that I've already said that before, so let me go ahead and get rid of that additional information there. I've already said it before, and we solve for theta sub d, and it ends up being 0.1798 radians. So now with a radius of 0.912 that corresponded to 50 sample periods for our settling time, and a zeta value of 0.456, which is coming to us from a 20% overshoot, now we have an angle theta sub d in the complex plane that's consistent with that particular zeta value and R value. Or it's 0.18 radians. We have 180 radians per pi, 180 degrees per pi radians. So we now have roughly 10 degrees of angle with a radius of 0.912 will satisfy our 20% overshoot spec and a settling time of 50 sample periods. But we didn't just have those two. We had a third performance specification, which was our peak time specification. The peak time specification, again, is time to peak is pi over omega sub d. We can solve that equation for omega sub d as pi over time to peak. Time to peak was 100 milliseconds, or a tenth of a second, or pi divided by 1 over 10, or omega sub d is now 10 pi. Just for fun, we can compare that omega sub d with our sampling frequency, which we already know how to compute that. That's 2 pi f sub s, or it's 2 pi over t, and we were given t. T was 1 over 100. So our sampling frequency, omega sub s, is 200 pi radians per second with a sample period of 10 milliseconds. That's really then only 20 times the damped frequency of oscillation, and for the given zeta value of 0.456, we actually have a natural frequency of omega sub d divided by the square root of 1 minus zeta squared. That actually ends up being closer to 35 And so now if you looked at 200 pi divided by 35, you'll see that we are only sampling at about 18 times what we would normally like to sample. I'm sorry, 18 times faster than our natural frequency. And we usually think about sampling, or the rule of thumb has been 30 times. We'll just keep that in the back of our mind. Now we're seeing that we're not sampling as fast as what we might ideally like to sample, but it's probably still livable with that sampling period. Now, based on this peak time specification, we've computed a damped frequency. That's 10 pi. What we want to do now is find the angle associated with that damped frequency. The angle is, say, omega sub dt. T we know, we just computed omega sub d from the peak time, or we now have 1/10 of pi, or just slide the decimal place to the left, and we have 0.314159 radians for the angle associated with the peak time spec. Or if we wanted to translate that into degrees, now we would say, oh, we have 180 degrees divided by 10, using theta sub d as 180 degrees instead of pi over 10. We now have this as 18 degrees. And what did we have before? Well, from our percent overshoot spec, we just had an angle of 10 degrees. So in this particular case, we can see that we don't have consistent performance specifications. Here, the percent overshoot specification does not yield a small enough time to peak, or peak time. Or stated another way, we could say that the peak time spec is more demanding than the percent overshoot spec. And now what do we do? Well, now I think it's helpful to go back and remember our geometric shapes. We have an angle from our percent overshoot spec. We had, well, that was based on this 0.45 logarithmic spiral. Then we also had a settling time spec, which gave us a radius of 0.912. So let's say that that's now here. Terrible circle. But now we can see that, in fact, our percent over, or our time to peak, was wanting us to have a larger angle. And what we want to know is, how do we get a larger angle and still satisfy our other two specifications? If we said we wanted less overshoot and we simply made zeta bigger, then that would mean that we would have a logarithmic spiral that's collapsing towards the real axis. And if we simply looked at that relative to the same radius, if this was our radius before, now there's our radius, we've actually made our angle smaller, and we wanted our angle to be bigger. What I'm hoping that you start to see is that if we moved along this constant zeta curve, then as we move along and increase the angle, we actually are shortening, or making our radius smaller between this point and that point. And making our radius smaller produces less settling time, which is usually in the direction that we are allowed to go. So in this case, I hope you can see that one way to approach this problem would be to reduce the radius. Our old r was 0.912. And what we want to now show is what r can we find that will allow us maybe to stay on this same damping ratio logarithmic spiral curve of 0.456 and yet reduce the radius, and by doing that we now make the angle bigger or allow us to achieve our settling time spec. Let's go through some of the different stages in this thought process that might actually come to mind and show you which way you might want to address that problem as far as which particular parameter do you want to adjust. Is it the zeta value, make zeta bigger? Is it reducing r? Or is it trying to now change your angle? Well, right now, we're actually trying to get a bigger angle by manipulating zeta or r, and I hope this last discussion showed you that by shrinking zeta, that's not going to help us, but by shrinking r and staying with the same zeta value, that's looking more promising. Let's now see, how do we find let's say an acceptable, how do we find an acceptable r to satisfy three specifications simultaneously? And let me just make a comment on what I tried to show earlier. If we looked at trying to reduce our overshoot by going with a larger damping ratio, zeta, this now gives us a smaller percent overshoot. Remember, our specification said 20% or less, so we could make zeta larger, but in fact, a larger zeta does not allow all three specifications, if we just change zeta alone, all three specs to be satisfied. Remember, we started with a zeta value of 0.456 using, or that arose from a 20% overshoot. Now, if zeta is increased, and we don't have to increase it much to give us a feel for what's going on. Suppose we increased zeta to zeta of 0.6, then what's the corresponding theta value? Well, theta sub d with zeta equal to 0.6 is now minus natural log of r over zeta square root of 1 minus zeta squared. Again, let's keep the same r value that we had before for our settling time specification, and that was now a 0.912, and this is 0.6, and this is 0.6 squared, and this now gives us a theta sub d of 0.1228, and before we had an angle theta sub d of 0.18 for a 20% overshoot. So we can see that we went from 0.18 to to an angle of 0.12. So in fact, our angle is getting smaller instead of larger as we increase zeta. Or theta sub d actually gets smaller instead of larger, with zeta equal to 0.6 and r equal to 0.912. So that says maybe we don't want to adjust zeta. Let's look at adjusting r, which is what I was trying to demonstrate earlier. Let's now look at reducing r, the radius, or improving our settling time or making our settling time faster. Let's look at reducing r to meet the 3 specs that we were given. So now we need to, for a fixed zeta value, or for a fixed percent overshoot, which in our case was 20%, and a decreasing radius, then you can see that if we stay on our logarithmic spiral and just walk around, then in fact we are going to be increasing the angle associated with that point as we progress or move towards the origin, or we shrink r and stay with zeta fixed. So for a fixed damping ratio or a fixed logarithmic spiral and a decreasing r, theta sub d, the angle actually increases, which is what we were wanting to have happen. What we want to do now is figure out what value of r can we pick, or should we select. Now, remember what we have already derived. We have this formula, theta sub d is now minus the natural log of r over zeta times the square root of 1 minus zeta squared. Well, we can now just slide things around in that right-hand side, and we can now say, oh, that's just minus the natural log of r, or let me go ahead and take that negative sign inside and put it downstairs with the zeta, so that I now have minus zeta downstairs, and upstairs I have the square root of 1 minus zeta squared. What do I know? I know the angle theta sub d that I want from my peak time spec. I know zeta that I want from my percent overshoot spec. I'm trying to find a smaller r value that will be compatible with those other two specifications. With this parameterized way of writing our angle equation, theta sub d, now with zeta equal to 0.456, which is consistent with a 20% overshoot, we can now plug that theta sub d into the bracketed piece of that right-hand side, and we now have minus the natural log of r, so I didn't put the negative sign there. Maybe I should go ahead and just leave it this way. And we calculate that bracketed piece with a zeta value of 0.456, and that now becomes equal to 1.952. Or we now know what theta sub d is from our peak time spec. That was 1/10 of pi. We now set that into the right-hand side, or therefore minus natural log of r is going to equal theta sub d, or 0.314159, divided by the 1.952, or that's now 0.1610 for the natural log of r. We can now take the anti-log of both sides, and we now have r is equal to e to the minus 0.1610, or r is now 0.851. So that now we started with our settling time spec of 500 milliseconds, producing a 0.912. Now we have an r of 0.851. What does this correspond to in terms of settling time, or what is the settling time for this new radius value r? And all we have to do is remember our settling time expression. That's r raised to n sub s in terms of power, and that's equal to 0.01. Now we know r, we know 0.01 on the right-hand side. Now we just solve for n sub s, and n sub s is now, we'll call it this ceiling function of -2. So we've now taken the log base 10 of both sides to give us the -2, and we have now the log base 10 of r, which this is now our new r value of 0.851. Plugging that value of r into this expression, now we have the ceiling function of 28.6, or now we are at 29 samples for a settling time. And if you remember, we wanted a settling time of 1/2 of a second, or 500 milliseconds, or that corresponded to 50 samples. Now, for this new collection of parameters with an r value of 0.851 and an angle theta sub d now equal to 0.314, now we have a settling time, t settle, that's n sub s times t, which is now 290 milliseconds, or 0.29 seconds. And since we wanted a settling time of 500 milliseconds or less, this now meets the 500 milliseconds settling time specification. And maybe what the take-home message from this example in terms of competing performance specifications might be is probably the easiest way to start satisfying specifications is to start shrinking your radius, or these concentric circles. That now allows you to maybe move along a constant damping ratio curve, and that now produces a faster peak time. And that's then what I would like to leave you with in terms of these competing specifications. You now want to be thinking circles, logarithmic spirals, and angles, and how do you make all of those different patterns meet the specifications simultaneously.